let's get started. Today we're going to be talking about the brms package. Continue to have to say this, although today and next week in particular, this is a bit misleading because it makes it sound as if I had anything to do with the brms package, when in fact that was 99% done by Paul Berkner, and the other 1% wasn't done by me. BRMS uses Stan to produce posterior draws from the models. The BRMS supports, so in a manner of speaking, this is not entirely wrong, but don't want to be perceived as if taking credit for something that Paul did, like I said, almost entirely by himself. And the reading for today has this flowchart thing describing the workflow for BRMS, much of which is or can be is by default done behind the scenes, but there are some aspects of it that you as the researcher need to handle. The first is the user, that being you, passes all model information to the BRM function in the BRM package. That's going to include at least enough information to define a likelihood function and specify priors on all the parameters in that model. BRM is going to internally call two functions, make stand code and make stand data. Both of those functions are exposed, so you could call them yourself. In particular, you might want to call make underscore stand code to read the code in the stand language. That BRM, or really the make stand code function in the BRMS package, auto-generated to translate the R syntax that you gave it. And the first step here to a program in the stand language, which we've referred to a couple times, might have quickly put up one example or so. So again, we are not covering the stand language in this class. It's not a particularly difficult language, but the class is particularly difficult, so it's just one less thing to have to cover. And as we'll see, if you haven't seen already, but you should have because it was in the reading, BRMS can do a huge number of models by generating stand code at runtime, piece by piece, kind of based on the information that you give it in the first. And then once you have once it's generated the stand code and prepared the data to be passed to stand, it's just a list, named list of things in R. It would be a dict in Python, whatever. That's all going to be passed to the the stand function in the rstand package. Then the stand code that was generated here is going to be translated again into C++, compile using the C++ toolchain that you all should have installed on your laptops, following the instructions of the post I did today on a discussion. And then Stan's algorithm is going to draw from the posterior distribution of that model, conditional on the data. Then the results come back to the BRM function in the BRM package, and I'll get assembled into a so-called BRM fit object, which is in many ways analogous to the stand reg object produced by rstand arm. which is kind of a glorified matrix of draws. It's really a list of a whole bunch of stuff. But that allows our functions to know what the model was and do a variety of useful things with the draws. Stan, like the C++ level of this, it has no understanding of what the data are or what the model is. You just kind of define the numerator of Bayes' rule. So it doesn't know what any of the variables mean. It's just looking at a whole bunch of numbers. And once it's done, that whole thing is, it's not inaccessible, but it's not very usefully accessible to do anything more. So what Orsten, Arm, and BRMS are doing is having these large fitted output objects, which have the draws that came from Stan, but also have a lot of information about what the model is. And so our functions can take that and do stuff with it that Stan wouldn't have been able to do on its own. And then the results can be investigated using various R methods that are defined for objects of this S3 class. So that's kind of the overview of it in this class, and in particular today and next week. We're going to be focused on the first part of it here and the last part of it there. But these steps exist, and to some extent you could do them one at a time if you wanted to. Once you feel the need to start learning how to do stuff in the Stan language yourself, it can be good to call make Stan code to see how BRMS would have done stuff. But it's auto-generated code. It's not really intended to be read by a human anymore. It's intended to make it rather easy for someone to do a lot of different things. But that sometimes means making code in kind of a formulaic way rather than the way a human who knows what they're doing would write the code, even though it might be equivalent to that. And so the main function in BRMS for estimating models is called BRM, it's short for Bayesian Regression Model. And unlike our Stan arm, where we have like Stan underscore GLM, Stan underscore LM, Stan underscore GLNB, several others, with BRMS there's just kind of one function. It's not intending it with its input syntax to be like quark for quark compatible with the negative binomial model in the mass package, even though you can do negative binomial models with BRM, and that's fine or whatever. It's just sort of intended to do its own thing, although the first 3 or 4 arguments are the main ones that you need to concern yourself with. Formula, the data frame, where the variables are, the family, which implies the likelihood, along with the inverse link function and whatever inside it, and the prior. There's a bunch more. Sometimes you need to use them, but we're going to mostly focus on those first 4 arguments today. So the formula arguments of the BRM, the things to the right of the tilde in the formula are going to be the same as in the rest of R. Maybe not base R, but inclusive of some other R packages. And so the thing to the left of the tilde is often just the outcome. But there are some situations in which you need to use a somewhat new syntax where y vertical bar, and then there's some function of another variable, and that function can be one of 5 or 6 things. Sense, which we'll talk about today to indicate censoring. weights, which is something that really shouldn't be used in Bayesian analysis. There's SE for doing a type of modeling known as meta-analysis, where you take a bunch of usually frequentist point estimates and their frequentist point estimated standard errors and do a model of those within some subfield to get a posterior distribution of frequentist point estimates. But in certain quarters, meta-analysis is really highly prized because people think of it as sort of saying, okay, what's the state of knowledge in this field, rather than being overly influenced by any one particular study, which is going to have whatever limitations that study has. But one of those limitations is like the estimated standard error and the point estimate are reported without any uncertainty. It's a point estimate. Trials, it's used in binomial models to specify how many opportunities there was. So like if you were doing this with the vetoes thing or the overrides thing, you'd be like overrides, vertical bar, trials, regular for the total number possible. Veto overrides, and then cat can be used in categorical models if there are more possible categories in theory than there are in the data. Well, there are more in like the population. There might be more categories than there are represented in the data, and so you can use that to specify what the levels of the categories are. But for the most part, the formula is the same as in R-stan-arm or the rest of R. Then, the data argument is literally the same. It's just a data frame or a tibble that has the variables that you're using in the model. The family argument to BRM can be one of a whole bunch of different things, some of which may have been referred to in the reading for some of the weeks. Others maybe not so much yet, but there are a lot of them, and each of these functions, like Gaussian or Bernoulli, really all of these, have a variety of choices for the link function or inverse link function. It's just flip side of the same coin. So if you put all those together, and that's not even totally exhaustive, there's a lot of log likelihood functions that you can use to draw from the implied posterior distribution using the MCMC algorithm and Stan via BRMS's extensive, essentially, translation mechanism from our syntax to Stan language syntax. And since these are, the Stan code is generated for them at runtime, you have to have a C++ compiler to do it. And oftentimes it takes more time to compile the model than it takes to estimate or to draw from the posterior distribution of the model for simple models. But that ability to generate Stan code at runtime means that you can proliferate the number of models that you can support quickly, although Paul's been doing this for several years now, as opposed to R-stan-arm and a number of other R packages that are on CRAN that come with handwritten Stan programs by a human that are precompiled. But anyway, it bears repeating, particularly if I haven't said it already, that just because you can do a whole bunch of models doesn't mean you should, and in particular, you don't have a whole lot of business estimating the parameters of a model that you don't understand. BRMS is not unique in this regard. You could easily point estimate frequentist models for any of these likelihood functions. It doesn't mean you understand what the model is. With machine learning, it's probably even easier to estimate a model that you have really no idea what it's doing, but it's producing point estimates, and those point estimates can produce point predictions, etc. And so a necessary and almost sufficient indication for whether you understand the model well enough to be able to draw from the posterior distribution of it is, can you draw from the prior predicted distribution of it and have those prior predictions look reasonable? And so both BRMS and our StanArm have the ability to do that for you, but that kind of pushes back, it kind of misses the point of demonstrating to yourself, or maybe to somebody else, but perhaps only to yourself, that you understand the model well enough, because you can generate from the prior predicted distribution of that model and have those predictions look reasonable when you yourself do it. And so that's what we're going to continue to emphasize doing every week, just like we have been doing it every week, even if we're going to use the BRM function to draw from the posterior distribution of the model once we have achieved a sufficiently nuanced understanding of that model. And so the BRM function has a prior argument, that's argument number 4, that ordinarily would be the result of a call to set prior, or it's more easy usually to just call the prior function, which has the same arguments. So if you call set prior, the first argument is going to be a character string in the Stan language. And the Stan language doesn't always parameterize these distributions the same way they are done in R. Like 80% of the time, yes, but 20% of the time, no. But if you call the prior function rather than set prior, you can omit the quotation marks, which are like disturbingly annoying. So that's what I usually do. And then there's a bunch of other arguments that sort of collectively indicate what parameters this call to prior or set prior pertains to. So there's like a class of parameters where you can specify the same prior for all of the things in that class, or if you need to be more detailed, you can specify the coef argument to indicate which parameter of the class things are pertaining to. There's a bunch of other ones that are used less often, lower bounds, upper bounds, etc., that may be on the parameters. But we'll see a few examples of how to call this. And so a very useful function in BRMS is the get prior function, which just takes like a formula, a data frame, and a family, and then it outputs what the default priors would be. So you can just source this macroeconomic data from week 7 to get the data set we've been using to analyze Fulton's law. And if you call get prior for a model where GDO is regressed on the change in the unemployment rate over the quarter using a Gaussian likelihood family, we see that the default priors are indicated here. Now, we haven't really been using the default priors even in our StanArm, and you really should not be using them on your homeworks or things like that, because at best, it should be impossible for someone like Paul or myself or Jonah that maintains these packages to choose a better prior than you can when we don't even know what the data is. Like, you should definitely be able to do a better job of choosing a prior, knowing what the data are and what question is intended to be answered by conditioning on the data, than people who wrote the package before the data were seen. So it's not as if like get prior looks at the predictors and like does something clever. It looks at the formula and does something kind of invisible. And one thing that's kind of on the edge of invisible is that the default priors for class B, which is the regression coefficients, have by default a flat, which is a euphemism for improper prior, which is not good. It's often not as bad in practice as it is in theory. But if you're using an improper prior on the parameters, that is sufficient indication that you don't understand your model, because you're not even able to say like what would be a reasonable set of coefficients and what would be unreasonable. In the case of Oken's law, anything positive for the coefficient on the change in the unemployment rate, not reasonable. Anything hugely negative, also not reasonable. So that's something that you should know, but it can't know by default, unless you tell it. Also, and we'll see this as we go along, BRMS is quite a bit flavored for psychology audience, although it works extremely well for non-psychology applications. But because Paul has a PhD in psychology and knows a lot of people in psychology who really like to use BRMS, etc., collaborates with a whole bunch of psychologists on their stuff, it has a psychology flavor to it. And the people who do Bayesian modeling in psychology, I'd say, can at best be described as reluctant using Bayesian methods. No more really than any other social science. But they're decidedly squeamish about specifying priors. And so to them, having the default prior be flat seems like it's a good thing, because it seems as if you're not specifying any information about the coefficient on the change in the unemployment rate or whatever psychology thing you're doing. But that's not true. It just seems true to people who don't really know what they're doing. So to specify an improper prior says every value of the coefficient is just as plausible as 0 is. And that would certainly include huge numbers, which are much more implausible than 0. This is like linear or whatever, but if we had an inverse link function that was like anti-logging this, another situation in which like even a number is like 20 or whatever, e to the 20th is something that never happens in the social sciences. And so these improper priors don't convey the absence of information, they convey the information that all parameter values are equally plausible, which is not true. It does not convey the information that all transformations of those parameters are equally plausible. That's also false. And it indicates that you as a researcher do not currently have a coherent set of beliefs about the parameters in the model that you are purporting to be an expert in, which is not a good look for purported experts. Even going back to the days of Socrates, who would basically just make fun of people who claim to be, experts in things, but immediately demonstrated that they are in fact not experts. So we have a proper prior on the intercept, student T distribution, 3 degrees of freedom, scale of 2.9 and or location of 2.9 and scale of 2.5. That also does not make a whole lot of sense. It is proper, so at least it integrates to 1. But student T with 3 degrees of freedom is going to have like excessively, for the most part, heavy tails. So Cauchy distribution is student T with 1 degree of freedom. So this is going to be slightly not as extreme as Cauchy. It does have an expectation and a variance, but it's super weak. And for the most part, you can do that. And then, another parameter is sigma, the standard deviations of the error in this model. That also has a student T prior with 3 degrees of freedom, but that's going to be truncated because sigma has to be positive. So really it's a half student T, taking away the negative part, just leaving the positive part, and multiplying the whole density by 2 so that the new thing integrates to 1 after you threw away the negative half. And that's also not necessarily a great prior. Most likely value is going to be on 0, which is actually the same as the exponential, but at least the exponential is kind of defined natively for non-negative values as opposed to truncating. Exponential is going to be asymmetric, whereas student T is symmetric before you truncated. Exponential, which is like the default in our stand arm, is the maximum entropy prior for a given expectation. Half student T is not. But anyway, so these are all dubious to various degrees, and that's in part a consequence of BRMS being able to support so many different models, and it can piece together all kinds of things to come up with something that maybe no human has ever really considered in great detail. And because it can support so many different types of models, it really can't make reasonable default choices for the priors on any or all of those models. And so, I would strongly encourage you to use not default priors when doing stuff with BRM, but I would also, McElreath or whatever, also certainly would encourage you to use maximum entropy priors if you're going to do some non-default stuff. So like I said, the class argument to prior or set prior refers to the type of the parameter in the model. B, which is kind of the generic prefix for a regression coefficient in a model. You've got intercept, sigma, others that we might talk about later. So anyway, a prior that's, I guess, equivalent or the same as the prior that we used before for this Okun's model situation. Normal -1, scale of 1, prior on the coefficient for the change in unemployment rate. So most likely has a negative association with GDO in a quarter. 3 with a standard deviation of a half on the intercept. BRMS uses the same convention as our stand arm, that by default the predictors are centered. And so the prior pertains to gamma, or the intercept relative to uncentered predictors, even though in the output the intercept will refer to alpha, or the intercept relative to the raw predictors. I think there's some way in BRMS to avoid that default behavior, but by default it does the same thing that our stand arm does in that respect. Then we need a prior on sigma, which, what we did before was, exponential with an expectation of 2, or a rate of 1/2. And so this prior business can be specified with pluses to like gather up priors on different parameters. That doesn't mean like addition in the sense of math. It's more like the ggplot use of plus to add another layer to the prior. Like this. So how will we do it? We can use multiple cores as usual. That's just a stand thing. And then we call BRM with the data Gaussian family in this case prior that we wrote on the previous slide, and you get out this BRMS fit object whose default summary / print method looks like this. It's a little bit different from what rstanarm shows. Like rstanarm, it's probably better to make a plot, which you can do rather easily. I'll show you how to do that in a second. But you can get this stuff. Again, with the understanding, you by default have 4,000 estimates of all the parameters. This is just an incomplete summary of those 4,000 estimates. This is not the estimate. Even though the first freaking column of this thing says estimate. So this is one of these like psychology flavored aspects to it. So what is estimate is actually average of posterior draws. In rstanarm, the thing in the first column is the median. This is the mean. Second column denoted here, estimated error. That in actual terminology, posterior standard deviation of the draws. And that's going to be the classic formula with the divide by n minus or r minus 1 in the denominator. It is not the median absolute deviation of the mediator scaled up thing, estimator of the standard deviation used by rstanarm, even though it's an estimate of the same quantity. You have the 1 minus 95% CI and the U minus 95% CI. Those are the bounds of the so-called credible intervals, even though they're made to sound as if they are confidence intervals for people such as psychologists who really like what confidence intervals, well, they really like what they think confidence intervals are, but what they think confidence intervals are, or what they mistakenly think confidence intervals are Bayesian credible intervals. So these again are the bounds of the thing that people mistake confidence intervals for. And so Paul, like a lot of people, labels those CI so that the confusion on the part of the user actually lands them in the right place, even though they're confused as to what CI means and what a confidence interval is. You get the bulk and the tail effective sample size. You can get those from rstanarm as well if you do summary. These, again, are estimates of the effective sample size concept that we have talked about before. These sort of separate out the effective sample size into the center of the distribution and the tail of the distribution. Often it will be the case, whereas rstanarm just kind of reports one overall one, but it will often be the case that the effective sample size in the center of the distribution is greater than the nominal number of samples due to the no U-turn Hamiltonian Monte Carlo sampler used by Stan. And so, yeah, by default it's still 4,000. That's actually a Stan default. And these are slightly estimated to be above 4,000. But in the tail of the distribution, it's often going to have a lower effective sample size. We're have less precision in our MCMC estimator about tail quantities than we do about central quantities. These are certainly plenty high in this case, and a lot of cases. But they're lower than the ones. Well, we get the same thing for what our standard arm would call auxiliary parameters. BRMS calls it family specific. Sigma, standard deviation of the errors, has a posterior mean of 2.5, etc. So anyway, main thing here is to not think of this as being identical to what our standard arm. It's another way of summarizing the 4,000 draws. Okay, next thing is the hypothesis function. So you can do this in our standard arm if you just call as Tibble and work with the draws. But because psychologists, if they love anything at all, it's testing hypotheses. So there is a hypothesis function for them. In BRMS, where you just call hypothesis on the object produced by BRM, and then you specify some kind of a string to indicate what hypothesis you want the evidence for. So again, even though this is hypothesis, and it is often misleading referred to as testing a hypothesis, we're not testing a point null hypothesis, or at least we shouldn't. Even if we're not doing Bayesian stuff, like we should not be testing a point null hypothesis. But with Bayesian stuff, we're ordinarily going to be evaluating, which is what I prefer to testing, a research hypothesis, the thing that we want to support, not the thing that we want to reject. And so in this case, we might be interested in the hypothesis that the coefficient on x, x being the change in the unemployment rate, is negative. What's the posterior probability of that? And so what comes out is a hypothesis, posterior mean, posterior standard error, bounds of the 95 or 90% credible interval thing, etc. And then post-prob, which is the proportion of draws where the coefficient on x is negative. In this case, is 1. So, as best we can estimate with 4,000 draws, we're sure completely that the relationship between change in unemployment and GDO is negative. And if this post-prob is like, it doesn't have to be 1, but if it's like sufficiently high according to some threshold, you get a star, which is really what the psychologists are interested in. Some sort of certification that the hypothesis in question is true. I think if the post-prob was like 0.89 or whatever, this might be a dot instead of a star, which is like part of a star except without the arms to it. So this is not doing anything that you haven't seen before. It just has a specific function to do so. There's also this evidence ratio, which in this case is infinite, which sounds really good. I think it's the ratio of the posterior density at 0 or to the prior density at 0, or the reciprocal of that. Prior density at 0 to posterior density at 0. Since there is no posterior density at 0, that is infinite. But in my opinion, that's misleading. Like, this is not misleading, it's just embedding it in this thing that tries to sound quasi-frequentist, but guide people in the direction of not doing frequentist stuff. You know. Questions? Okay. So with BRMS, you can do the same estimator of the expected log predicted density using Pareto smooth importance sampling, leave one out, cross-validation. And really this stuff you can do with RStan ARM as well. We just didn't have time last week to get into it. But you call it the same way, really. So we call Lou on the objects produced by BRMS, and there's a plot method for the objects produced by loop, which you can specify label points equal true to see a plot where the vertical axis is the estimated Pareto shape parameter in the Pareto smooth imported sampling process. That was referred to in the reading for last week. On the horizontal here, we have an index for the data. This is in chronological order. And so, as was mentioned in the reading for last week, when the Pareto shape parameter is estimated to be greater than 0.7, the implied estimator of the ELPD is not good. And in particular, when the estimate is above 1, the estimator of the ELPD is not valid. It doesn't have a finite expectation, should not be used. That does not mean the posterior distribution is in any way invalid, although it might be. But it does mean the Pareto smooth imported sampling leave one out cross-validator of the expected log predicted density of n future data points is invalid. And in particular, when you get into a situation like that, you should be looking at what points the posterior distribution is too sensitive to in order to sustain the Pareto smooth imported sampling leave one out cross-validation estimator of the expected log predicted density. In this case, quarter 201 and 202, starting in 1970. So this would be the quarter for the onset of the lockdown due to the pandemic, and this would be the quarter immediately thereafter. So like I said, doesn't mean your posterior distribution is necessarily flawed. But it does mean using that posterior distribution to estimate the ELPD with the Pareto smooth imported sampling leave-one out cross-validation estimator is invalidated by the fact that the posterior distribution is so sensitive to the first quarter of lockdown that we can't really estimate that thing right from the whole posterior distribution. And so that may be, and well, it is something you would want to consider, especially in the context for Oken's law. So one, again, Arthur Oken did not intend to specify a law. He specified a regression. His students and other followers and whatever started calling it Oken's law. But neither Arthur Oken nor anybody else would have a brain intended the model for the relationship between GDO and the unemployment rate to apply to situations in which essentially the whole country was not allowed to leave its house and go to work. This is way beyond what Oken intended his regression to be applicable to, which was, mostly normal times, perhaps inclusive of normal recessions, but not due to we decided no one's working for a while. In part because such a situation was never reflected in the data that Oken used to originally specify this regression. Closest thing was Spanish flu during 1918, 1919, whatever. But one, they didn't have lockdown orders really, and two, they didn't have data on GDP and whatnot at the time. Nowadays, we retrospectively have estimates as to what economic growth was in 1919, but in 1919 they didn't. And Oken was doing this in the 1960s or whatever, so he didn't have data on that period. Anyway, Oken did not intend Oken's law to be applicable to 2020. Now, it might kind of be by accident. but that wasn't intended. And so to use the data from the pandemic to support or oppose Oken's law as like a heuristic for thinking about the economy is a bit questionable, just on scientific grounds. But we could take 2020 out. That wouldn't be the worst thing in the world. But what's perhaps even better is to call loop with moment match equal true or reloop equal true, both of which implement alternative estimators of the expected log predicted density that don't rely on the assumption that the Pareto K thing is less than 1 or less than 0.7 or whatever. And so this moment match is a little bit faster. ReLU is actually easier to understand. They're both intended to do the same thing. So if I'd said ReLU equal true, it would refit this model twice. It would leave out the quarter 201 and refit it, and then it would do it again, putting in 201 but leaving out 202. So it would do literal leave one out cross-validation for just those two. And for the other 200-ish more, it would use the Pareto smooth reported sampling leave one out cross-validation estimator for those. But it would do literal leave one out cross-validation for these two. And thereby come up with expected log predicted density for all of them. Moment match tries to do something similar, might be a little bit quicker. But anyway, once we do that, then we're in better position to do posterior predictive checks using intervals in this case that are based on this leave one out concept. Literally in the case of these two, estimatedly in the case of all the others, but all the others satisfy the assumption, so that's cool. And we see what we saw before, namely that when the economy or when the country, whatever, went into lockdown, what Oken's law would have predicted would be somewhere in this realm of negative 40% growth. In fact, as best the government can guess, the government's model wasn't intended for a pandemic either, but like what is reported now as the government's estimate of the change in GDO during the first quarter of lockdown, closer to negative 35%. So although that is outside the 90% predictive interval of Oken's law, I think we should stop to appreciate what Oken did. Again, he did not intend it to be applicable to pandemic. But the fact that you can get anywhere close, what's really the difference between negative 40% and negative 35% growth for an economy? So, kind of by accident, Oken's law was not horrible for the first quarter, even though it did not actually include the observed GDO, in part, probably in large part, because during lockdown, we paid people who weren't going to work an actual, decent amount of money, which is not something we do under normal periods, even for people who are disabled or whatnot and can't go to work. We give them practically nothing. So the fact that we were essentially giving income subsidies to people who couldn't go to their job at Starbucks or whatever is one compelling reason why the reduction in economic growth was not nearly as bad as what Oken's law would have predicted, because a number of people got a fairly decent amount of money even though they weren't going to work. and they can continue to buy stuff on Amazon or whatever. Similarly, first quarter after the lockdown, economy rebounded with 25% or whatever growth reported by the government. That's greater than what Okins would predict, in part because people saved some of the money that they received from the government, and so they had to spend it once things started to open up a little bit again. But also because like all this stuff that didn't get made in factories and whatnot during the first quarter of lockdown, there was a catch-up immediately in the quarter afterward. So that turned out to be a little bit higher than what was predicted by Okins law, but again, it was in the right ballpark. So maybe you should keep those two data points in, but you should use moment match equal true or ReLU equal true in order to get a valid estimator of the expected log predicted density, because your results are somewhat sensitive to those two quarters. Probably like more information came from those two quarters than all 200 other quarters put together, which is, you know, whatever. But when you have the right Pareto's estimate, K estimates, then you can do this plot that we were talking about last time. Last time when we were doing like the election, national election study thing, it did not look so good. This one looks pretty good. So you certainly can achieve good calibration. This is based on taking the Pareto K things, putting them into the Pareto CDF, so getting numbers that should be distributed uniform if the model is well calibrated, comparing it to a bunch of draws from a uniform distribution, which are these background little gray lines, and they look extraordinarily similar. So Okins law, even through the pandemic, well calibrated if you use the alternative estimator for those Pareto things. Anyway, many of the things that you can do with the objects produced by BRM are the same, or at least analogous to the things that you can do with stuff produced by RStanArm in terms of like as array, as data frame, as matrix, you know, other things, coef, log, shiny stan, Woo, as we saw before, posterior EPRED, posterior predict, all that stuff. Anyway, there's like 90 different things that you can do with a object produced by BRM, and those are often very similar to what you could do with objects produced by RStanArm. All these functions are just defined for the S3 class BRMS fit, this glorified matrix of draws, but contains a lot of meta information about the model that allows these functions that you call afterwards to do their thing, because they can query this for like, what's the model? Okay, so let's think about some models that you could do with BRMS that you cannot currently do with RStanArm. One is the so-called categorical logic model for outcomes that are defined on a sample space. They consist of the integers between 1 to j, which we think of as labels rather than numbers. So classic social science example of this would be what brand of orange juice do you buy from the grocery store? So your grocery store includes capital J brands of orange juice, and the grocery store collects data on which brand of orange juice you buy. One of those. Or if you don't like orange juice, maybe none of those, but we could expand the model to include people who don't like orange juice, but whatever, they're weird. So let's just think about this. Among orange juice drinkers, do you buy like Sunny D, Tropicana, whatever other types of orange juice there are. So what's the math notation for a model like this? Well, the outcome we observe is a brand of orange juice from 1 to j. And we're thinking of that as the largest among the values, eta plus epsilon. So we have eta that's indexed both by consumer, person, and j, brand of orange juice. And then we're going to have the corresponding errors. Those errors are assumed to be drawn from a standard Gumbel distribution, which we have not encountered yet, but no big deal. It's a probability distribution. Happens to produce errors that work well in this situation. So we can think about this as like Y star, or utility for orange juice. You buy the brand of orange juice, or the observed brand of orange juice that you buy is presumed under this model to give you the greatest utility among all brands of orange juice, but it could certainly include the price. So maybe you prefer the not most expensive brand of orange juice because the most expensive brand of orange juice is too expensive for you. But there's some other brand of orange juice that's not as expensive that you like also. And so taking into account like both the cost and the taste and the vitamins and whatnot, you might get more utility from one brand that might not be the most expensive one, whatever. So eta has the usual form. We can write this relative to the raw predictors or with the substitution that we've been doing before, make the intercept relative to the centered predictors, in which case we can interpret it as expected utility for a person with average predictors and orange juices with average predictors. So you can, in this model, also have like orange juice specific predictors, like the price or the amount of vitamin C, or does it have pulp, or things like that. So you have predictors that are properties of orange juice, or predictors that are properties of individuals, such as their income, or whatever. Do they live in Florida where like orange is the state fruit? And then we have priors on the intercepts and the coefficients. Only difference in this case being we have an intercept and a set of coefficients for every brand of orange juice. This model specifies your utility over all capital J brands of orange juice, which is particularly important if you have orange juice specific predictors. Like if you didn't, then you could do this model, but you might not if you only had like individual level. And so this is not so different from what we've been doing before. Indeed, if J were 2, this exactly simplifies to the data generating process for a Bernoulli logit model. Because the difference between two standard Gumbel distributions is distributed, or standard Gumbel random variance is distributed standard logistic. In which case we just interpret like 1 relative to 0 in terms of like which thing do you choose, Romney or Obama, etc. But these models are most useful when J is greater than 2. In which case we need to specify utility for all brands of orange juice. But this is in contrast to models that we'll talk about next week, where we can put some sort of ordering on the brands. This is a situation in which we have capital J possible outcomes, but no obvious order. So like, we could order the juices alphabetically, but that wouldn't be scientifically relevant. Now we might be able to order the juices by like where they appear on the shelf in the grocery store. But let's just say no. So no order here. How would we draw from the parameter? So let's take 1,000 draws, whatever. So we have to have a prior on 3 different intercepts relative to uncentered predictors. So we need a mean and standard deviation for that. I set the standard deviation for the first one, so little j equal 1, to be 0 for identification purposes. And that's not something that we've talked about before, even though it actually was relevant to some of the models that we were talking about. So we can see from this notation for the generative model, well, one, we could multiply this by any positive constant and not change which is the maximum, right? We could multiply all these by 5 and the observed data would be the same. So that's why we use standard Gumbel with a scale of 1 rather than estimating that scale, because if we did, the scale would be undefined. So we just fix it to 1 and sort of estimate coefficients and intercepts relative to that. We actually did that with regular logit model, we just didn't talk about it at the time. It's a little bit different about these categorical models with j greater than 2, or greater than or equal, but specifically greater. We could also add a constant to each of these and not change the observable data. So we could add 5 to all the utilities and people's choices of orange juice would all be exactly the same. That's really just another way of saying what is said often in economics textbooks and whatever, that utility is only a relative measure. It's not an absolute measure. It's only useful for saying which the differences in utility for different orange brands as a guide to what people purchase, rather than conveying something in absolute units. And so by putting priors on the intercept that have no variance and an expectation of mean, it's essentially constraining the first gamma j to be 0, exactly. And then everything else is estimated relative to that. And that breaks the lack of identification that would have otherwise have occurred. So anyway, we got prior on the intercept, prior on the coefficient. And for each of the 3, let's say, brands of orange juice, we can create a tibble that has intercept and a coefficient. You can do this with more than one predictor, but here I'm just doing it with 1, and that's going to give us 3,000 draws. 1,000 draws for the intercept and the coefficient for each of the 3 purported brands of orange juice under consideration. So then how will we draw from the prior predictive distribution? Well, we're going to have to do it one brand of orange juice at a time. Group by brand of orange juice, then do it row-wise. And so for the jth brand of orange juice, we're going to get an eta, gamma plus beta times x, presuming x has already been centered. Keep track of which observation, because we're going to need that later. Then, once we're done with all that, all the 3 brands of orange juice, we're going to draw errors from a standard Gumbel distribution, which can be done by taking draws from a standard uniform, the logarithm, so that's going to be a negative number. Negate the logarithm, so that's going to be a positive number. Take the logarithm again, which may be positive, may be negative, and negate it again. Convoluted process, but it's not even really that convoluted, but that's what characterizes Gumbel random variables. And then we can group by observation and simulation and form a realization of y as to which of the 3 gives us the highest utility when we add the 3 etas to the corresponding 3 epsilons. And thus the output of this would be a data frame with n by 3 by capital R rows, and the outcome y would be 1, 2, or 3, which again we should think of as labels rather than integers. They're merely indexes for the 3 brands of orange juice being considered. Okay, if that's a generative process, it is a generative process. But if that's the generative process we're considering, what's the log likelihood that's implied? Well, as it turns out, the probability person N buys jth brand of orange juice can be shown to be mu sub j, which is e raised to the power eta j, divided by e raised to the power eta for all summed up over all capital J brands of orange juice. So it's really like e to the eta relative to the sum of e to all the etas added together. So this is going to be a number between 0 and 1, which it should be, if it, or it must be, if it's to be a probability in this model. And then the log likelihood is relatively simple. It's just the logarithm of the product over all the data. So the logarithm turns the product into a sum. So we have a summation over people. We have a summation over all capital J brands of orange juice. We have an indicator function, which comes down from the numerator, or the exponent, when you take the logarithm of it. So the indicator function does person Y, in fact, purchase orange juice brand little j. Again, indicator function returns 1 if that statement is true, 0 if that statement is false. And so when it is true, we have 1 multiplied by the logarithm of the probability that the person purchases the little jth brand of orange juice. When this is false, we just have 0 times the probability that they chose some brand of orange juice that they did not, in fact, buy. So that is the log likelihood for this model, and this model is called categorical, at least by statisticians. It is unfortunately often referred to as multinomial by non-statisticians, which is to say machine learning people. So statisticians reserve the phrase multinomial to refer to the sum of categorical variables, the same way binomial is the sum of Bernoulli's. So that's binomial Bernoulli, that's a special case where j is 2. This is a generalization where j could be greater than or equal to 2. But if you're just modeling like one person, or each person individually, I mean, I guess they could buy more than 1 carton of orange juice or whatever, in which case you could consider a multinomial. Well, let's just say they buy 1. So then it would be what we call categorical, and that would make sense. So I did not actually have a data set on orange juice, and could not find one readily available. So let's do this with another data set that comes with R, and is therefore easy for you to follow along with this example, which is very famous, might even go back to Fisher, about irises, which is a type of plant. And this famous data set on irises has the species of iris. There's 3 different species considered: Setosa, versicola, and virginica, whatever. And the task is to predict which species of iris the nth plant is, using information about the length and width of its petals on like the flowers of it, and also the length and the width of the sepal, which I think is like the neck of the plant. So as usual, when applying an inverse link function that has e to it, you're going to want priors that are pretty concentrated towards 0. Otherwise, you're going to get into a situation where it's like, I'm sure that this is probability 0 or probability 1, when that is probably not warranted. But anyway, so we get set up some weakly informative priors. In this case, we have to avoid, in order to avoid a warning from brms, we need to specify which of the little j's these priors pertain to. Remember that we had to specify eta for all the brands of orange juice, but actually we're restricting the intercept and the coefficients to be 0 on the first brand of orange juice for identification reasons. And BRMS does the same thing. So we're only modeling an eta for the last 2 species of iris, and we're sort of considering the first species to be a baseline. And so to do that, we need to indicate not only what class of parameter we're trying to pertain this to, but also the part of the model. So the expectation for the probability that your versicolor iris or a virginica iris is a function of these things. Anyway, specify a formula, species predicted by everything else. In the iris data set, we specify family equal categorical, whose default link function is log, like it had on the previous slide, etc. And then we indicate which priors pertain to that, and you can plot the parameters if I hadn't been signed out. Amen. You can plot the parameters, which, as I was saying, is probably better than looking at a table of posterior expectations and posterior standard deviations and bounds on the 95% CI and things like that. However, as with all of these all of these generalized linear models, or things that are like generalized linear models, the parameters are going to be in units of eta, or at least eta 2 and eta 3. Eta 1 is fixed to be 0, and it's kind of the baseline category. So we can make this plot, and we see that we have a lot of uncertainty about the intercepts. But the coefficients on sepal length and sepal width and petal length and petal width are considerably more precise, although in some cases essentially straddling 0. But we have coefficients on sepal length, sepal width, petal width for both the versicolor and the virginica species. So although you can make these plots, they're in units, and you have to model j minus 1 of them. It's not as if we have really a great way to interpret any of this, except to say that the wider the petals, the more likely it is to be a virginica iris than it is to be a baseline iris, which in this case was setosa, or whatever. Okay, so among the things that you can use after you've estimated one of these models is posterior epred, posterior predict, etc. So you can call those the same way we have done them before. You can either do it with new data, which could be counterfactual, but if you don't specify new data, it just produces the posterior expectations for the data that you used to condition on, estimate the model. So in this case, it's going to produce an array, 4,000 draws on each of 150 observations. There's 150 observations on different irises in the iris data set, and 3 levels of species of iris. And we get the posterior expectation of each of them And for every row in observation, these three probabilities are going to sum up to 1 by construction of the inverse link function. So yeah, these are numbers between 0 and 1. They are expectations, which is to say probabilities in this case of discrete choice outcome as to what species of virus you choose to be. It makes more sense in social science data where we think of orange juice as more of a choice than the flower's choice of what species to be. That's in part why the way in which I sort of set up these generated models may differ from what you see in the company's reading. But you can also get posterior predictions, which are draws from the categorical distribution with probabilities produced by posterior ePrim. And so this is going to be R by N matrix. And the elements of that are integers, not real numbers between 0 and 1. They're going to be 1, 2, or 3 indices of the 3 levels. So one thing that brms does that I'm not so much a fan of is it produces predictions that in R are of class integer. And that tempts people, particularly psychologists, to do ridiculous things with the predictors, like say the average of the 1, 2s, and 3s or whatever, even though there's no such thing as like an average iris. But these are really just, I prefer the entries of this, which they are in R, were Setosa, versicolor, or virginica rather than 1, 2, or 3. It means the same thing, but in R, if you call like mean or something on the predictors, you'll get an error if those are actually like words. Whereas if you call mean or median or whatever on these indices, you'll get back something that makes no sense. Like the median of 1, 2, and 3 being 2, but the median iris is not versicolor. There's no such thing as a median iris. Those are not numbers. So we should not be applying interval or ordinal concepts to them. But one thing we can do is take the probability of them being these 3 different species of iris. Those are real numbers, probabilities, between 0 and 1. Inclusive, but they're usually internal to the 0-1 interval. And we can join those with the actual observed species from the data. We have to copy that the appropriate number of times in order for it to be 4,000 by 150 or whatever, but then we can use those to make the plot that appears on the next slide here based on the posterior probability. So given the plant's petals and sepal, which again I think is like another name for like the neck of the plant. Not that the plant is breathing, but whatever, the stem of the plant. Given that information, essentially all setosas either have probability 0 or probability really close to 1. So in the language of machine learning, the petals and the sepals or whatever provide a lot of information with which to discriminate setosas. So I don't know exactly how, but the model does. If you give it the information on the petal and the sepal, it can tell you pretty much for sure whether this iris is or is not a setosa, based on the characteristics of its petals and its sepals. The other two, there's certainly some that have a pretty much 0 probability of being versicolor or virginica, basically because they have a probability very close to 1 of being setosa. But these have a much less pronounced bump toward the high end of the probability, which is to say, given that we have iris whose petals and sepals disqualify it from being a setosa, we're not as sure as to whether it's a versicolor or a virginica iris. Evidently, they have very similar petal length and width and sepal length and width. I think they have like different color flowers, but we're not considering the color of the thing in this model. So, given the information that we have, we're certainly less able to say for sure that one of these things is a virginica or a versicolor, and that's reflected by those. So we can do a plot of the density of the posterior probabilities facet wrapped by outcome in order to get a better understanding of what's going on here that honestly was not forthcoming just from this, because this is the units of eta, and what we really want are probabilities, but we got to apply the inverse link function to this multiplied by the coefficients to get the probabilities in order to plot them like we have done here. So questions about this? Questions about any of this? BRMS, Opens law, plants. Question about plants?
Yeah. Sorry, what is the mu in the x-axis here?
So that is the probability of a plant being each of these three species. If you look in the mu, those are going to add up to 1 for every combination of the first two, of like the rows and the columns. For any row in column, you'll have 3 numbers, and those 3 numbers are all positive, and they add up to 1. And they are respectively the probability of being setosa, the probability of being whatever the second one is, versicolor, and the probability of being virginica. And because those are the only 3 possibilities being considered here, those add up to 1. So mu is the expectation of the outcome if you think of the outcome as being coded in dummy variables. So you have a 3-column outcome. Dummy variable for setosa, dummy variable for versicolor, dummy variable for virginica. Now, we don't input the outcome that way. We give it a factor that's like setosa, versicolor, or virginica. But you could think about it as like a 3-column thing with dummy variables, which is often known in the machine learning literature as 1 hot. So in that 3-column matrix of dummy variables, all but 1 will be 0 and 1 will be 1, which indicates which of the 3 species of iris this was. It's not a super efficient way of representing the outcome, but if you think of it that way, then each row has an expectation vector for the probability of it being each of those 3 things, and those probabilities should add up to 1. They should be not negative, etc. And that's what the generative process and the posterior distribution, when you condition on the observed plants, implies. So this generative model implies the probability that you buy little j's brand of orange juice or plant in is setosa or whatever is mu indexed by j, e to the eta j divided by the sum of e to the eta whatever. So this is going to be between 0 and 1, which it is in the posterior distribution, or the posterior expectation. Oh. Yes?
What would the unit of eta be in this case?
It's if j were capital J were 2, it would be log odds. But when j is capital J is greater than 2, it's not log odds anymore. It's just, that's kind of the problem of these GLMs. It's the units that imply mu as probability. But that's kind of a backwards way of defining it. It is respecting positive versus negative. So like I said, looking at this, if the petal width is large, that has a positive effect on the probability that it is a Virginica, and a negative effect on the probability it's a Setosa. But how positive also depends on the other one, versicolor. So when you have more than 2, there's even less of an interpretation of the parameters. Obviously, I mean, the intercepts are very uncertain, but the coefficients are pretty close to 0. And that underscores something I had said previously, but because I was underscoring, I should probably say it more than once, which is you should interpret models rather than interpreting parameters within models. So we can always, always, always ask posterior egret, posterior predictions or whatever to get stuff out in units that from the model in units that are understandable. So these are probability that the plant is this or that species. That we got. Or if we deal with predictions, you know it's going to be 1, 2, or 3 that stands for Setosa, versicolor, or Virginica. Okay, that's a type of plant. If you were a gardener or whatever, you'd probably understand what that means. So we're not forced to interpret stuff that's in units of eta. Eta is just this intermediate thing. Now in linear models, eta and mu are the same thing. So you kind of get the false sense of security that you can always, you know, interpret beta in like Oken's law, you know, in isolation from any other predictors. But it doesn't work that way in general, particularly for models that have these nonlinear inverse link functions, where the probability of any one thing depends on everything in the model, rather than giving you isolation or separation or anything like that. But we can always interpret the model by interpreting posterior distribution of the expectation of the predictions or something like that. And if necessary, I could graph, you know, the probability of this against one of my variables. It won't be a linear, straight line, but it would have probably like a monotonic or otherwise fairly predictable relationship between versicolor and something. Probably even more so if I included the color of the flower thing, but anyway. Question?
So if you're using these plots to kind of make a statement, do you just have to frame it like proportionally? Like for around mu 0.5, you would say between versicolor and Virginica, it's about the same probability.
Yeah.
Is that consistent?
Pretty much. There might be a little bit of a discrimination, but I think basically they have about the same size. They just differ by color. Whereas a Setosa differs by size from the other two. So given the size characteristics, we can tell for sure whether it's a Setosa, pretty much for sure, whether it's a Setosa or not. But if it's not a Setosa, then we're not really at all super sure as to whether it's versicolor or Virginica, given the information we conditioned on. But probability of all those things adds up to 1 per plant. So you said it was in proportion terms. That's a little bit frequentist. Like they're probabilities, subjective probabilities. Like those are your beliefs as to whether this plant is Virginica or whatever.
Where they're not the probabilities across the plants? Because they don't seem to have one.
No, for
each
any one
individual.
plant, like if I had a plant here and I was like, what species is this? You'd be like, oh, it's a probability 0.6, it's a versicolor, and probability 0.39, it's a virginica, and probability 0.01, it's a setosa, based on the size. Other questions? So again, main thing I want to keep re-emphasizing is that this is not so different from what we've done before. Indeed, if capital J were 2, this would be equivalent to a Bernoulli-Logit model. And we'd just be considering the first thing to be the reference category and the second thing to be the, like with the Obama and Romney thing. Slight generalization to the case where J might be greater than 2, but we don't have ordering to leverage. Okay, it's another type of model. Survival model, which sounds like a television show or something, but it's actually extraordinarily common in public health, epidemiology, other things like that, where they spend like 20 out of 24 hours per day modeling how long it takes someone to die. In social science, we might, or other parts of social science, we might think of other things, but it's all about how much time does it take until an event happens. With public health, the event is always somebody dies. But in other situations, we could maybe think of something a little bit less morbid than that. And survival, otherwise known as duration modeling, was mentioned at some point, one of the previous weeks in McElvey's reading. Because, at least from the perspective that we've been pushing in this class, it's not so different from the other sorts of models we've been considering, but it's got some tweaks to it. Namely, we're defining the outcome that we observe to be y star if y star is less than some known constant c, and c if y star is greater than or equal to c. So what is c? Well, in a typical public health situation, you study people and you record, how much time after the start of the study did they live until they died. But some people manage to keep kicking until the end of the study, until you run out of grant money. So all you know from the data set is the person was still alive when the data recording people stopped recording data because they ran out of money. So it's not as if a reasonable public health model should be predicting that people are immortal. It's not a good model out of sample. So it's not as if these people never died. Just they didn't die before the study ended. They lived up until the end of the study. But C, the time after the start of the study when the study ended, is ordinarily known. It might even be a constant for all observations in the data. So what this means is if the person died before the study was over with, y is y star, which is the amount of time it took for the person to die. But if the person didn't die, we know that they survived at least up until time c. Could have died the day after, but if they did, it wouldn't be recorded in the data because the data stopped getting updated yesterday. Okay, what's y star? Well, when modeling time it takes for an event to happen, we ordinarily think of time as being non-negative. In which case perhaps we should use a distribution defined for non-negative random variables, such as the exponential. Now, in fact, the exponential is kind of a restrictive choice to use in this case, but it is maximum entropy So you can make a McElvey/James style argument to justify using the exponential distribution, and the exponential distribution has a conditional expectation, and that conditional expectation is the reciprocal of the rate, and so the rate is the reciprocal of the expectation, mu. So what's mu? Well, the expectation for how long it takes someone to die should also be positive. So we need to be applying an inverse link function that maps real numbers to non-negative real numbers. And that is typically the antilog function. Doesn't have to be. There's other functions that map real numbers to positive numbers, but the one overwhelmingly used by frequentists is the antilog inverse link function. So let's define mu for the nth person to be e raised to the power of eta for the nth person. And then we can do the usual thing with eta, have an intercept relative to centered predictors, a bunch of coefficients multiplying the centered predictors, etc. Normal, it doesn't have to be normal. I always use normal, keep it simple. But let's say normal. Prior on the intercept and each of the coefficients in this model. So, except for the fact that this is a non-negative random variable. So like GDO can be negative. So like normal was a reasonable choice there for the error. Time until something happens can be really negative. So, we got to use a distribution that's appropriate for that, but also censoring the fact that some observations don't die until after the study over is a fundamental characteristic of public health. And so, like, the counterparts of you in the public health school, first day of graduate school, they learn not to just do something stupid with the observed. Why? Average time until death or something like that with the observed values. Because the observed values include people who are not yet dead. And so the average of the observed Y's is going to be a downwardly distorted estimate of the amount of time people in whatever situation are expected to live. So that's something we got to deal with in the modeling process. But this observation mechanism is part of the process that generated the data we have. It's just there's a cutoff of C on the top. So questions about the setup here? So the code to draw from the prior predicted distribution, normal on the intercept, normal on the coefficient. You can have more than one coefficient, obviously. Let's say C is known to be 6 years or whatever. The study went on for 6 years, maybe. We take draws, size R, from these normal distributions on our parameters. We go row-wise, and then generate a summary, even though the summary is larger than the input. We get eta, gamma plus beta times the centered x. If there was more than one x, we'd do more than one term. Mu is the antilog of eta. Y star is drawn from an exponential distribution with rate 1 over mu. And then we take y to be the minimum of y star in C in parallel. So for each person, it either comes out to be y star if y star is less than C, or C if y star is greater than or equal to C. So we observe outcomes that are continuous and not normal, not even conditionally. But also we know that the data that we observe is censored at C. Questions about how to draw this? question about how to draw this.
Well, not so much to draw it, but the generative model itself. So y star, we have distributed exponential because it needs to be positive, right? And then, but we're saying the expected value, like the rate is one over the expected value. We have the length function, but the eta is log odds, which means it has to be positive anyway, right? So I guess
So eta is not log odds. One, we're not modeling the binary does someone die or not. That's guaranteed to happen eventually. There's a time until you die. So this eta is more resembling the eta in a Poisson negative binomial thing with the anti-log inverse length. But this is not a count either. You can die at any time, even though the data might actually be like recorded to the near the day or something. In principle, it's a continuous thing. So again, eta is, and consequently gamma and beta, which are in units of eta, is less than interpretable. It is, eta can be interpreted as the log of the expected survival time. So the log of the expected y star, but it is not the log of the expected y due to the truncating. So we can interpret y star in this case as actual survival time in reality, even though the study only observes survival time up until C at most. So in this case, yes, you can interpret eta as the logarithm of survival time, and consequently gamma and beta are in those units. But as with anything involving anti-log inverse link function, if you're not real particular about your priors on gamma and beta, you may very well be putting positive probability on someone living to like 1,000,000 years. It's not something that you want to be putting very much probability on. So anti-log inverse link function is kind of regrettable. Mathematically, it's easy. Everyone, like not everyone, a small percentage of people understand that the anti-log produces a positive number and like survival time should be positive or whatever. But in a lot of social science situations, it's easy when applying an anti-log inverse link function to get something that is scientifically way too big. And so you got to convey that to the model. Well, gamma and beta are going to have to be pretty small, if not negative. All right. So if that's the generative process, what's the log likelihood for a survival model? Well, if y(n) is less than c, we observe the survival time exactly, or as exactly as it's measured. But if c is equal to yn, then we know yn is less than y star. The time you are observed to survive is less than the time you survived in reality. So we observed a lower bound on your survival time. And if we were Bayesian, or we are Bayesian, but we could consider the y stars for people who are not dead yet to be unknown parameters. So for the people who are dead, y star is beta, and for the people who are not dead yet, y star is a parameter with this prior. And we could just consider the y star for the undead people to be additional unknown parameters and draw from the joint distribution of their true survival times as well as gamma and beta. And that would be fine, and Stan could do that well. It's not what frequentists do. And so for better or worse, Arslan RMS, etc. are going to follow what frequentists do whenever that's not like completely ridiculous. And in this case, somewhat reasonable to write the log likelihood like this. So the sum over all the observations. Indicator function if y is less than c, which is to say the person is observed dead. That's 1. And it gets multiplied by the logarithm of the PDF, in this case exponential, although you oftentimes see people use other likelihood functions besides exponential in it. But if yn is equal to c, which is to say person n is not dead yet by the time the study ends, then we add the logarithm of 1 minus the CDF evaluated at c, the logarithm of the probability the person survives longer than c given their eta, or the anti-log transformation thereof. So this is for the dead people, this is for the people who were still living at the time the study ended. No big deal. Like I said, exponential is kind of a rare choice in this context. You'll see other distributions on positive random variables being used, such as Weibull. But the essence of it is the same, starting from the bottom, working to the top, applying an anti-log or some other inverse link function somewhere along the way to make sure your conditional expectation is positive if you're modeling survival time, whatever. But also in this, you always have to deal with censoring. It's just almost all situations are going to have censoring. So as an example of doing one of these with brms includes a data set called kidney, which has data on 76 people whose kidneys were failing due to one of these other diseases that I don't even know what they mean. We got age, we got sex, we have the time until their kidney like totally failed or whatever. And then we have another thing which is a sensor indicator. So rather than saying C or whatever, it just says 0 if the person was not censored, 1 if they were censored. Which is to say they haven't died yet by the time the study ended. I don't really know about priors, but I think they should be pretty small. The way in which we specify this in BRMS is time, vertical bar, which doesn't really mean given, it just means vertical bar. And then the censoring indicator is given by this, 0 if not censored, 1 if censored. And then let's say that's a function of age interacted with sex. Let's make dummy variables for which kidney disease the person has, given the exponential family whose default link function is log. And there's my weekly informative priors. Can get this stuff at the end. All looks good as far as effective sample size, and here we get this posterior means, but it's going to be in units of eta, which, like we said, not a whole lot. Also, we can see right away coefficient on age was real small. That is in part because I didn't do my usual thing, which is to put age in decades rather than years. So for some things in public health, like a year can make a lot of difference. Like, it doesn't sound that way, but the difference between an 82-year-old and an 81-year-old is actually like a pretty big deal, lifespan-wise. For these people, they're not that old. They're just, kidneys are failing for other reasons. Anyway, the coefficient on age comes out to be like 0 to 2 decimal places. I should have put it in decades, but whatever. So let's say we didn't look at the summary and we wanted to understand the effect of age. We can get posterior egret, applies the inverse link function, so this is going to be in units of time, but there's no censoring in the posterior expectation. This is the expectation of how long you really live in reality, not how long we observe you to live in the study. We can get the lower 5% quantile and the upper 95% quantile, columnize those along with the median, combine those into the data set and make a plot that you see on the next slide here, which has different facets for male and female and for the 4 types of kidney disease being studied here. And as you can see, the effect of age is nothing. It could have been more interesting, but honestly, like if you're a 20-year-old whose kidneys are failing, that's indistinguishable from a 21-year-old whose kidneys are failing. It's not because of your age, it's, you know, because of something else. Anyway, out of time, need to get out of here. I'll post the 4th homework tonight. It'll be due before class next week. Get into the using BRMS, also the stuff from last week. And, you know, as usual, Tuesday have office hours and review session.